Alright, I'm gonna start recording in 3, 2, 1. Hello, welcome back to the second video in the avionics web series through the Society of Astronautics and Rocketry at the University of Pittsburgh. So this is the second video, Circuit Basics. My name is Yahya Farag. I'm the avionics lead for the 24-25 year. In the previous video, which I recommend you watch if you haven't, we kind of went over what this whole series will be about, and this video is going to be the background and linear components section of the core subjects subset, I guess. So here's our introduction to linear components, and to begin, we're going to talk about voltage, current, and power. So if you've taken an introductory physics course, these things might be really simple, but I think it's good to reconceptualize them and make sure we have a holistic understanding. So voltage is the potential of charge or electrons from one point to another, and the general conceptual understanding we're going to use in this series will be water. So the voltage can be thought as the potential of water in a water tower. So we're going to assume here's kind of our floating mass of water, and this value from the ground, which we'll call our reference or our ground, is going to dictate how much potential we have. So if this is V1, we can come to the assumption that something up here can be called V2, and obviously V2 is at a greater potential than V1. So it really has nothing to do with the amount of water. If we're starting to think of amount, that's when we can conceptualize current. So the current is the rate of flow of electrons or charge, and that reflects in the units of current, charge per second. And the way we can think of this is how much water is flowing in 1 second. All right. Don't know why I did that, but we're just going to continue. Okay, I cleared my screen. Great. So we can kind of go back to what we were saying, that current is kind of how much flow we're getting in t seconds, right? So more current means more charge in 1 second, less current means less charge in 1 second. And then the way we really differentiate is this concept of power, which is a little harder. The general equation is that power is equal to the voltage times the current. And what this helps us understand is, we'll go back to the water tower example, is even if we have a super high potential, if the flow coming out is pretty slow, the power might be different than if we have something at a pretty low potential but really high flow coming out of it, right? So the power pretty much is that voltage times our current, and helps us compare these two to see which one is greater. And it's just a way of comparison, right? So one of the two core concepts, KVL and KCL, is kind of our introduction to circuit analysis. We'll start with KVL, which I think is the easiest. Its general definition is that all current entering an electrical node must equal the current exiting it. So the first concept here is the concept of a node. So you can think of this as a wire. This is our node, and we have another wire. And obviously it would make sense that the current going in here is going to be the current coming out there, right? It's a wire. But KVL is particularly useful. So if we have a node where it splits, the kind of law is that if this is I must equal I1 plus I2, which is a very intuitive understanding. which is why it's pretty easy. And the conceptual understanding, we'll go back to our water example, is if we have a pipe and the pipe splits off into two and then rejoins, the amount of flow is going to stay consistent at the end. So this flow will have to equal that flow, right? And it's just an extension of the conservation of energy. The next general law is Kirchhoff's voltage law, which is a little harder to visualize than KVL, and that's why I like, or KCL, sorry, that's a typo. And that's why I like to go with KCL first. The definition of KVL is that the sum of all voltages in a loop must equal 0. So the conceptual understanding for this is that in a closed loop or a closed system, the voltages kind of all have to cancel out. But that still doesn't make like a lot of sense, and that's why I like to run with the water tower example again, is that say we have 2 water towers, right? And we're kind of just scanning the system as a whole. We'll kind of scan, we'll go up, so that, let's assume that's 2V, so we added 2V, and then we have to go down, so that's minus 2V, and then we'll go up by V, and then we'll go down by minus V, and then we've summed up our system. We've created kind of this loop we were talking about. And if you add up the changes, which is all voltage is, it's a potential change, it's a difference, then the voltages in our loop all sum up to be 0. So we're going to introduce some of our components. So our linear components, which we also call passive components. And in this video, actually, we are only going to cover resistors and capacitors. The main characteristics of a passive or a linear component is that they're cheap, small, and pretty simple to use. They're called linear because there's a linear relationship that they have with voltage or current. So the two we'll talk about in this video, and it's passed out again, is we're going to talk about resistors, and that's the symbol for a resistor, and the capacitor. And the learning objectives for this video really is what each one is, what they do, most importantly, how to use them, and we might go in a little on how you would pick one when you're designing something, right? So the resistor is the simplest component. This is the symbol for it. It resists the flow of current. You can think your mental model of a resistor is a wire with resistivity, which is P. So the resistance is equal to the resistivity times length over the area. So if you treat the resistivity like what it is, a natural property of the material you have it made out of, copper, carbon, whatever, you can change the resistance by either making it longer to increase, right? So as length goes up, your resistance will go up, all kept constant. And if you want to decrease your resistance, you could either decrease your length or you could increase your area. So if you want your resistance to go, so as your area goes up, your resistance will go down and vice versa, right? The law that kind of dictates how a resistor behaves is Ohm's law. And pretty much what it states is that the voltage across a resistor is equal to the current through it times that resistance. So we're going to treat the resistance as something that's almost fixed. So the conceptual understanding is that when you lock R, as you apply more and more voltage, as there's more of a voltage drop across it, more current will flow through your resistor and vice versa. And then less voltage means less current. So when you analyze a circuit, you'll often see the current flowing through the resistor I, and then some voltage drop or gain, but almost always a drop, which is V. And then you make your equation V equals I times R. And then some more conceptual understanding is that if you lock the V, so your voltage is unchanging, you want less current, you increase your R, You lower your R, you're gonna get more current. And you could also lock I, but in general, what we'll learn is that you don't really see a constant current in the types of circuits we build in most power systems. But you can use the relationship, Ohm's law, to derive the conceptual understanding. So let's combine some resistors. So the idea of series resistors, which means anything that's in series means the components line up. So you have a resistor, R1, and you have another resistor, R2. The series resistors add up to make an equivalent resistor. So we can kind of combine these two resistors into an equivalent resistor whose value is equal to the sum of all the resistors in series. So R1 plus R2. It's very simple. And the opposite of that is parallel resistors. So that's, you can think of that as components stacked up adjacent to each other. So it'll look something like this. Here are our parallel resistors, and you won't see them in this configuration as often, but it's important to understand that the voltage across these will kind of be the same, but the current will kind of split up if you're imagining the current flow going through them. And when you add them up, you can still create an equivalent resistance. So R1, R2, R3, your R equivalent will be equal to a single resistor that's smaller than any of these resistors. So it's going to be smaller than R1 or R2 or R3, and it's going to be more often than not, or always, smaller than the smallest resistor. And the equation to calculate this is that the equivalent resistor is equal to the inverse of the sum of the inverses, which is kind of an annoying equation, but it'll help us in the future. So probably one of the most common applications of a resistor in avionics particularly is a voltage divider. So that means two or more series resistors with a voltage source. So say we have some voltage applied, V out, and then we have our two resistors, R1, R2, or this should be V in, sorry. And then we'll just call this our ground or our reference, or 0, right? And then reference from 0, we're going to have some V out. This V out is equal to V in times R2 over R1 plus R2. So what this means is we take V out will always be a lower, like less than V in. It's being split, right? It's dividing it. So for example, if R1 is equal to R2, so 1 ohm and 1 ohm, and V in is 5 volts, you can do this equation, but generally if they're equal to each other, V out will equal to 1/2 V in, and you can substitute that in the equation. So this will be 2.5 volts. So you can tune V out to be the voltage you want by changing those resistor values, the ratio of the resistors, right? Next is the current divider. So we touched on this. You don't see it as much, but conceptually, what's happening here is that we have two or more parallel resistors, and by tuning the values of R1 and R2, we can dictate how much current is going to, the ratio of current split I1 and I2. So we know I1 plus I2 is equal to I, but if we want the ratio of them, we can derive R1 and R2. And if you want a challenge, you can derive that yourself, or find a resource that explains them more in depth. It's just not something we use very often compared to the voltage divider. So another application of a resistor is as a current limiter. So a resistor in series with another component will set the current in the loop or in the branch. So you can think of this as some voltage going in. You have a V, or a source of voltage and current, V comma I, entering into a black box component, and then maybe like going to ground, right? I will always be equal to I because it's not splitting up anywhere. So you can set the current by putting that resistor there in series. And the most common application of this in our case is a LED. So if you have a 5-volt source and you have an LED, which is a diode, and we'll talk more about diodes in a future video, and I want to set this current I because the LED can only take some maximum, I can set that current given a set voltage by putting a resistor and tuning that value to be less than our maximum. Moving on. So a capacitor, like we saw, there's its symbol. It's actually more common in designs. You'll see more capacitors than resistors more often than not. And essentially what a capacitor does is it stores charge. So true to the symbol, a capacitor is essentially two conductive metal plates with area of the plates and some distance d in between them and some dielectric epsilon. So the dielectric constant, similar to the resistivity, is just kind of something that's always going to be the same or set by the manufacturer or something like that. But the values we can play around with is the area and the distance. So as the distance decreases, the capacitance will increase. And as the distance increases, the capacitance will decrease. And then the same idea with the area. You can kind of derive that for yourself. But the equations, similar to how Ohm's law dictates how a resistor works, they're capacitor equations. So the base one is that the charge in a capacitor, so the low charges stored inside this dielectric and the electric field in between, is equal to the capacitance times the potential between the two parallel plates, so the applied voltage, right? So more voltage means more charge in the capacitor. This equation isn't very useful, but it is useful if you take its derivative. So if you look at how it changes over time, what you can get is that the charge over time, over seconds, is equal to the capacitance, which is just similar to the resistance, an inherent property of the component, is equal to the voltage change over time, right? So then what this equals, if you recall, current is the charge per second. So we've just come up with a relationship now similar to Ohm's law with resistors for capacitors, and that means the current in a capacitor is proportional to the capacitance times the derivative of the voltage. But this doesn't really, even personally, this doesn't really mean anything, because you're like, oh, voltage, is it a function? What is it, right? So to better understand this, we kind of have to understand frequency and its relationship with derivatives. So this is going to get a little hand wavy, but we'll go through it pretty slow. So frequency and signals. So let's define a signal. A signal is a finite or an infinite signal that represents our voltage in time, right? So if we look at our y-axis, we can define it as voltage. Our x-axis is our time. You could simulate a switch turning on and off for a second as the voltage, say, V1. Our switch going high at 1 second, right? And then low at 2 seconds, which means, our switch was on for 2 seconds, right? This is what we would define as a finite function, right? Another example of a voltage signal could be a sinusoid. So this is an infinite signal, but pretty much it's a sine wave that's, for all intensive purposes, going off to infinity, right? And for both of these functions, at every single time, it's going to have some derivative. So this is much easier to visualize with the sine function, where here at the top, for both, the derivative is 0, and then at the bottom, the derivative is also 0. But something like right there, you can have a non-zero derivative that's going up or down, right? And that's how this is the derivative of our voltage function at any time, right? But that's kind of a pain to do, to look at our capacitor at every single time, especially if we're applying an infinite function on it, or a function for a really long time. So a sinusoid, if you can recall the equation for it, you could write it as sine omega t. So t is obviously like our function, so y of t, right? And then our amplitude of our sine wave is equal to v1, right? So then we have this omega term, which is our angular frequency. And from our angular frequency, we can kind of derive our just general frequency and our period. So it's easier to think of it as the period, because that's a real thing you can measure. The period could be like 1 second, the time it takes for the signal to kind of fully return to where it once was. So that's 1 period, right? And then you can kind of back calculate. You can get the frequency, which is the inverse of the period, and you can, from the frequency, you can get the angular frequency, right? Which is 2 times pi times the frequency. And really the conceptual concept that's the hardest to grasp here is relating this idea of frequency and the derivative. So the derivative, especially if you haven't taken a calculus course, is kind of a really, hand-wavy concept. But if you kind of nail down that it's the rate of change at any time, then let's just suppose that we have blocked off 1 second. For a period of 1 second, right, our sine wave will look something like this. So that means our derivatives aren't, they're changing, but they're not changing too often, right? You can, if you really you can kind of almost call this like a box, right? But in that same 1 second, a signal with a higher frequency is going to look like this. And this is, kind of hyperbole. But now you can notice, oh wow, the derivative is changing super often, more often, right? So we can kind of derive the fact that as the frequency goes up, we can kind of just wave our hands and say, yeah, the derivative dv over dt is going up. dv over dt. The average derivative is going up, right? At any time step we grab. So taking this relationship, we can recall that the current is equal to the capacitance times the derivative. So if we assume that the capacitance is a constant natural property, we can say that the current of the capacitor is proportional to the derivative, and now by extension the frequency of the voltage applied. And this is best shown through an example. If we just have our capacitor in our circuit here, and we have, for example, we apply V1, and this is what V1 looks like at 5 volts. This is our V1 function, right? It's a DC, it's unchanging, it's always 5 volts. That means our derivative is 0. That means the current in this capacitor, I, is 0. But say we have an AC signal, which means in general our derivative is greater than 0. So we'll call this V2. We have our capacitor to ground, and this is what V2 looks like. We'll just say a sine. We can assume that we now have non-zero derivatives at all these times, right? And then we can kind of make the assumption that I will be some value greater than 0. So not greater than or equal to. It must be greater than 0, right? So the big takeaway here is that at low or 0 frequencies, the capacitor is going to act as an open circuit. So something where no current is flowing through, right? And at higher frequencies, the capacitors will act as a current, or will act as a short, or kind of we can model it as a resistor. And that's kind of the concept of impedance, which isn't super important to us, but it's definitely something worth taking your time to learn, as it'll really solidify this concept even more. So assuming your frequency is going out to infinity, then your capacitor will become more and more like a short circuit. So its essential resistance will approach 0, and it'll just become a short circuit. So what is the biggest application of a capacitor in our type of work is what we like to call a decoupling capacitor. So in general, we like to say that our sensitive chips and electronics like a DC voltage supply. So kind of like in our example, we really like a nice clean voltage. So if here's our voltage, here's our time, this is good, right? But that's not always the case. What our voltage will often look like is it'll look like this 5 volts with some fuzz or noise on it. And this is what we like to refer to as high frequency noise. So it's kind of like on top of our signal. So as this high frequency increases, we want less and less of that current to enter our chip. So let's kind of draw this. So if we have our black box, which takes in our voltage signal, our Vin. Am I going to have to redraw that? Yeah, well, it just cleared. So we have more space. So as we try to take in our Vin into our system, here's our capacitor. Here's our black box. If we give it that clean voltage it wants, V, no current will flow through the capacitor, and all the current will flow into our sensitive black box electronics. But say as we get more and more high frequency noise, we want that stuff to go through the capacitor. So let's redraw it one last time. So we have our capacitor. We have our sensitive electronics. We want our high frequency Vn. We don't want any of this stuff, right? We don't want any. So we want all the current to go through. And this is kind of our KVL, which is you kind of have this current going in and out. They're going to sum up. But the ratio, when it's DC, you want the ratio to be all of I. And when it's AC, you want it to be all of I in the capacitor, right? So the general rule, the takeaway here, is that for every single power pin on a sensitive electronic device, a chip, add a 0.1 microfarad capacitor. And the value doesn't really matter, just it's a rule of thumb. But it's good to know what the capacitor is essentially doing here is it's taking the high frequency current and voltage and putting it to ground and allowing the DC voltage and current to go into our sensitive electronics. So that was some basics. Thank you for watching the video. In the next video, we are going to move on to active components. And this will help us fully conceptualize what we're going to use these linear components for, but they do work hand in hand for the systems we want to design. Thank you.